Hello everyone, welcome to this presentation. I am Siddhant Raja, a fourth year undergrad at the Indian Institute of Technology, Delhi. I worked on this project during my summer research internship at the University of British Columbia. On behalf of my co-authors, I'm going to present our work on exploring bimanual teleportation in virtual reality. Here is an outline of today's presentation. We'll be looking at the relevance of hands-only teleportation, see some related works and identify the research gaps, look at how we address these gaps through our work, discuss the study design and tasks, highlight the key findings and provide design guidelines, indicate the scope for future work, and finally conclude with an ending note. Firstly, the introduction. In many 3D VR applications, one of the biggest challenges is for the player to navigate the 3D space. Teleportation is a widely used navigation technique appreciated for its adaptability in confined spaces and its lower motion sickness impact. In teleportation, users generally use controllers to point to the destination and use controller buttons to perform various teleport actions. Modern VR devices are equipped with hand tracking technology that enables users to perform VR interactions without needing a controller. Researchers have shown that this greatly increases our immersion. Therefore, recent research has shifted towards controller-free teleportation, leveraging this hand tracking technology. Now some related work. In a recent work, Chowdhury et al. Designed a technique named rearm that combined wrist and arm movements for controlling the teleportation parabola. This resulted in better performance than arm-based methods. However, they did not explore the potential of two-handed input, nor did they study the effect of user posture. Building on the established merits, we extend this technique in our work. Given the prevalence of teleportation, evaluating the potential of bimanual input is essential. Here, bimanual refers to two-handed interaction where each hand has a distinct role to play. To the best of our knowledge, the only work that compared bimanual techniques to unimanual ones was carried out by Schaefer et al. In 2016, which concluded that there is no clear winner. However, they performed a limited comparison by considering only the right hand for pointing, neglecting the left hand in bimanual techniques, and considering only a timeout-based approach without gesture-based triggers in the unimanual ones. Moreover, they focused on basic tasks involved large targets placed at constant distances on the ground level, which does not represent realistic scenarios. We perform a more comprehensive evaluation of the bimanual techniques involving varying target distances, sizes, and elevation. The choice of user posture in VR has been found to have a significant impact on the overall user experience, including comfort, immersion, and locomotion. In the VR teleportation context, Sarupuri et al. Found that task scores were higher while standing compared to sitting, and that a majority of users preferred standing since it gave them more flexibility. However, no prior work has studied the effects of hands-only teleportation, which involves moving the arms and performing gestures while keeping the hands elevated as opposed to holding the controller in a static position supported by the lap or the desk. We try to find which hands-only teleportation technique is the most effective for VR teleportation. We study the impact of user posture, sitting versus standing, on performance and user preferences. Although Fitts law provides a guiding framework to evaluate interface designs or interaction techniques, no previous work has utilized it for teleportation tasks in VR. We not only make use of Fitts law to evaluate our designs, but also propose a new variation that is more accurate than popular existing ones. Now let's look at the user study. Before we discuss the study design, we'll have a look at the study procedure to have a mental map of what's really going on. The task here was to teleport from the current location to the target location designated by a sphere using a hands-only technique. The selection ray, parabola in this case, emanated from the wrist and was manipulated using the wrist and arm movements. The color of the target sphere and the selection ray changed on an accurate selection, providing visual feedback. The confirmation was triggered using a gesture or timeout based on the technique used. Once confirmed, the user gets instantly teleported to the selected location. You can observe this in the video as the trees get closer at the end of the trial. In each trial, the timer starts by selecting the start button indicated by a blue cube here and ends with the selection of the destination target. We recorded this as the movement time. Now let's discuss the study design. We have two primary independent variables, technique and posture. We use a Latin square design to counterbalance the technique posture combinations. The combinations of target size, distance and height resulted in 8 index of difficulties as per Fitts law. Each condition was repeated 5 times for each technique posture combination. We recruited 20 participants for the study. As handedness is a potential confounding variable, we involved only right-handed participants. We recorded the movement time as discussed earlier, the error rate as the percentage of trials with errors over the total number of trials, and the end point deviation, which is the shortest distance between the target sphere's center and the parabolic pointer during a successful selection. We used the MetaQuest Pro headset as a test bed and Unity for development. Let's have a look at the techniques that we explored. The technique on your left is right pointer right gesture, RPRG, wherein the teleportation parabola is controlled with the right hand and the same hand is used to confirm a selection by performing a closing the index finger gesture. Using the same hand for both tasks reduces the user's cognitive load as they do not need to mentally switch between the hands for different actions. However, we anticipate that this technique will lead to more errors as the users might accidentally confirm selections while intending to point. This is known as the Heisenberg effect of spatial interaction. In LPLG, both tasks are performed using the left hand. We anticipate that this will be slower than RPRG because participants who are exclusively right-handed in a study are using their non-dominant hand, which could result in longer teleportation times and higher error rates. In right-pointer dwell, instead of gestures, a timeout-based confirmation is used, where users keep their pointer hand still for a certain threshold time to trigger a selection. We anticipate that this technique will offer more stability and comfort to the participants as it does not involve sudden hand movements. However, the timeout duration might lead to frustration for easily reachable targets due to a long wait time. Bimanual techniques, as the name suggests, involve both hands to play distinct roles requiring coordination and control, which might lead to steeper learning curves. However, once learned, we expect these techniques to outperform unimanual techniques as users can point and trigger using different hands, offering more control and stability. We conducted our trials in both standing and sitting postures. An office swivel chair was used to allow unrestricted movements to the participants in seated position. We used 4 Fitts law models to analyze our data to predict the movement time. The first one is the standard Fitts law model. Here, the target amplitude A is the distance between the midpoints of two consecutive targets with radius W. The constant A and B are empirically determined. We propose a new formula where we incorporate the effect of target depth d, the horizontal distance from the origin, and height h, the elevation. Intuitively, the lesser the target depth or height, the easier it is to select, and lesser the moment time. We divide the target width with the maximum of depth or height to capture the apparent width of the target as observed by the user. We also compare this with the two-part model proposed by Shoemaker et al. And the Vergence accommodation model. For more details, please refer to our paper. How did the models perform? Interestingly, all the four models managed to capture our teleportation task accurately with an adjusted R-square value of greater than 0.85. However, we observe that our proposed model outperforms the other three models based on R-square, adjusted R-square, and AIC values. Let's have a look at the results of our study. Naturally, lower target heights lead to significantly lesser trial time, and larger target widths lead to significantly more accurate solution. Overall, RPLG, LPRG, and RPDW are significantly more accurate than the unimanual gesture-based ones. RPLG resulted in significantly lower moment time while ensuring high accuracy as per our expectations. Interestingly, it was faster than even LPRG, which can be attributed to the natural alignment of certain tasks like pinpointing or stability with the dominant hand. RPDW was found to be as accurate as bimanual techniques and even more for easier tasks, such as targets located at lower distances and heights. However, RPDW demonstrated the highest moment time owing to the threshold dwell timeout one must wait to confirm a selection. For preference scores, we took 7 subjective criteria from the NASA TLX questionnaire and 2 additional subjective ratings, preference and fatigue. Friedman tests showed that there was no subjective difference between the two postures, sitting and standing. However, we did find significant differences between the techniques. Pairwise comparisons revealed that LPLG had less preference, more effort, and more overall demand than the other techniques. We provide some guidelines to VR designers on the basis of our findings. Considering the superior performance, we encourage designers to incorporate bimanual techniques for teleportation in their applications. Also, aligning tasks with the dominant hand can significantly enhance user experience and efficiency. Our proposed Fitts law model outperforms existing models and considers key aspects of user behavior in VR teleportation, leading to more effective design solutions. While the RPTW technique, a dwell-based one, demonstrated high accuracy, especially for simpler tasks, it exhibited significantly higher moment time. Designers should exercise caution when using dwell techniques, particularly for applications where speed is crucial. The study did not find any significant difference in performance between sitting or standing. So, VR applications should be adaptable to both postures, allowing users to choose based on their comfort and the type of experience they seek. Now, let's discuss some scope for future work. We explored a limited set of target attributes based on pilot studies and previous research. Future studies could incorporate a wider range of combinations. We also did not include other pointer types. A straight line pointer has been shown to have advantages for mid-air targets. We did not look at the long-term usage of hands-free techniques for teleportation, which might lead to fatigue and other physiological issues. Researchers could investigate the ergonomic feasibility of hands-based teleportation. We adopted a simplified task to help participants focus on teleportation without visually searching for targets located off screen, a design typically used in Fitts law studies. We encourage future studies to incorporate more complex tasks, including virtual rotation and visual search. This slide summarizes our findings. Finally, I would like to emphasize that complete controller-free techniques are crucial to providing natural interaction capabilities to users. This warrants further investigation into hands-only teleportation that allows users to explore near and far objects in the virtual environment with ease. I conclude with the hope that VR designers incorporate our suggestions into their applications to provide users with a seamless, immersive, and lifelike experience. Thank you. Please refer to our paper for more details. Should you have any questions, feel free to contact the authors.